Welcome. Thank you for attending this talk, for listening to this talk on lattice dynamics in low-angle twisted bilayer graphene. I'm going to talk to you about vibrations and a specific signature of vibrations in twisted bilayer graphene. The outline of my talk will be as follows. I will first talk to you about phonons in generality, tell you a little bit what is so peculiar about vibrations in layered materials, and then explain to you how we can computationally handle very large twisted bilayer graphene supercell. Of course, I will explain to you what a twisted bilayer graphene is while we get there. And finally, I will conclude with some consequences explaining the phonon bands, the particular vibrations we find in those twisted bilayer graphene, as well as the experimental verification that we were able to get for this. So the first topic is phonons. A phonon is a vibration. In fact, the simplest vibration is that of a diatomic molecule that can be seen as simply two masses and connected with a spring. And so the force constant K of the spring is basically a measure of the strength of the chemical bond between the two atoms. And we know how to solve this problem. Of course, the frequency is square root K over M. So if you know the masses of the atoms, you can have a measurement, with spectroscopic measurement of the vibrations, will allow you to understand, to get an idea of the force of the bond, basically. Of course, most of the time, the materials we look at go beyond a diatomic molecule. For example, we have a solid, or we have some 2D system. But again, the idea is the same. To calculate the phonons, we imagine that the interaction between the atoms can be considered as a kind of a collection of springs, not just first nearest neighbor, but a collection of springs. And we calculate the force constant in a way I'm going to mention in a second. But the point is that we end up getting the vibration, the collective vibrations of the material this way. And there is a one-to-one correspondence to the entire vibrational signature of the material and the material itself. So we can learn a lot of things about the property of the material. So we will work in the harmonic approximation, and we are going to look at the unique signature of the material. So I can tell you a bit more about the harmonic approximation. The harmonic approximation is that when we write the Born-Oppenheimer potential, that's so the potential between the ions in a solid, that it can be expanded around the stable position, so the equilibrium position R0, and stopped at the second order in the perturbation. So that's what we mean by harmonic approximation. We don't go further and anharmonic effect. Of course, the first order disappears since we are at equilibrium position where the force is at 0. So what we do computationally, we calculate the second derivative, and when we build what's called a dynamical matrix. And this dynamical matrix, which has a size of 3 times the number of atom, can then, its eigenstate of the dynamical matrix, we have the eigenvectors, which are the normal modes of the material of the vibration, and the frequency, which is the square root of the eigenvalue of the dynamical matrix. Gives us all the vibrations, and we can calculate this for different Q points in the Brillouin zone of the material, and then we get the phonon band structure. Of course, depending on how we calculate V, so the potential between the atoms, the problem becomes more or less difficult. Also, depending on the size of the system, we can use more accurate or maybe more practical solution for using V. I'm going to mention 2 of them in a minute. One thing that's remember is that we want to have access to these vibrations through measurements, like for example Raman spectroscopy or infrared spectroscopy. Now, one thing I like to say is that when we solve these equations, like a wave equation for the phonons, we introduce a solution which is e to the power I omega t, and this explains the time evolution of the vibration. Now imagine that for some reason you calculate a frequency that's imaginary. In that case, the time evolution will actually show a decaying exponential or an increasing exponential. In fact, it can be either. And that means that the structure is not dynamically stable. So it so happens that when you have complicated energy landscape, if you are not sure that your structure is completely in a global minimum, or if you have lots of numerical instabilities, you can end up with negative frequency. I mean, with complex frequencies, which are represented as negative frequencies, the Phonon band structure. So we have to be careful about that. Now, we can look at the low frequency, and those can be used to probe interlayer interactions. So let me try to explain to you a little bit what we mean by low frequency interlayer interaction. So if you consider your two layers like this, represented in two colors, they have their own intrinsic vibration, internal vibrations, and you can consider that the interaction between them can be described by those springs. Of course, those springs are going to be pretty low force constant, since they correspond to low energy interaction, like van der Waals interaction, for example. And that means that if you look at again this ratio square root k over m, that number is going to be very low, much lower than the vibrations, the internal vibrations that we see inside internal to the layers. And so those frequencies are very small and used to be not easy to measure. Now they can actually be measured by many Raman spectroscopes, and the advantage of them is that they can interrogate the interaction between the layers. So this is a very important thing. I'd like to explain to you a little bit more in MOS2. This is a Phonon band structure for MOS2, and we can see that we have three acoustic modes, of course. And those three acoustic modes correspond to a full translation in the three direction. One perpendicular to the layer, and two in the plane of the layer. Imagine that you put two of them together. If you put two layers together, so before they get coupled, so imagine the two layers are far away from each other, nothing happens. But what happens if you put them together? They can either move in phase, or they can move out of phase, and completely out of phase. So this one in phase is still an acoustic branch. That means that at gamma equals 0, they still move rigidly, but when they are out of phase, the vibration is actually interrogate the spring, because it elongates and compresses the spring, and this corresponds to a breathing mode, a low frequency breathing mode in van der Waals 2D layers. We have the same effect for the two other acoustic branch, which are the shear modes, and those can lead to either one acoustic mode or a shear mode, because we have a movement of a shear between the two layers. And now, of course, doubly degenerated, since we have a two-dimensional material. Those shear modes have been measured in this paper in 2012. This is the blue line. They've been measured for different multi-layer graphene, so in AB stacking. And this number, it's indeed changes with the number of layers, as we could expect. And so this is a shear mode. So these shear modes have been observed. In fact, it's been observed a number of times. This example here is a work that was done with Shi Ling, who's now at Boston University, and in collaboration with my group doing a theory. And there we were able to predict the breathing mode in few layer black phosphorus, and the vibrations are a bit higher frequencies, because they correspond to a stiffer interaction between the layers as expected for black phosphorus. We have something similar for MOS2, where we can observe both the breathing and the shear mode depending on the number of layers, because they have different symmetry, and so they have different Raman selection rule. We can measure all this, and in fact they've been measured in many structures, many 2D material, and we produced a pretty comprehensive review of everything up to 2017, a few years ago, with my students Yang-Bo Liang, and where we explain how those measurements can be made as well. So and the theory behind them. So I invite you to look at that reference if it's something that's of interest to you. But what I'm interested in this talk is the twisted bilayer molybdenum twisted bilayer graphene, but we also look at twisted bilayer molybdenum disulfide. And so here, the work that was done by Shengxi Huang, who is a professor at Penn State University, and this is a collaboration we had with my group as well. What she did there was able to rotate one flake on top of another, and was able to look at different angles as shown on the right-hand side of this plot. If you look at the Raman shift for this high frequencies, these are considered high frequency in Raman, fairly high frequency, there's not much happening, there's no much changes. However, if you look at the very low frequencies, or around 20 wave numbers, you see there is a lot of changes in those frequencies. And in fact, those bands correspond to the shear and breeding mode, as I mentioned to you in a minute ago. And so all those branches can be explained theoretically. These are fairly small models, so we can do it numerically with density functional theory, so quantum mechanically, and can be explained by the presence of different domains in the Moire super lattice corresponding to the rotation, to the rotation of one layer compared to the other. But the topic of this talk, after this long introduction, is to talk about graphene with a twist. And the work I'm presenting has been published most of the work has been published in this paper by Michael Lamparski for his thesis. So of course, graphene with a twist, twisted graphene, people have seen this for a long time, for a number of years. It's well known, but the idea is that if you rotate one layer on top of another, you see those superstructure happening. And those superstructure, so periodic new crystal lattice, if you will, are called Moire patterns. And this is the topic of interest for me in this particular talk. Of course, the reason why twisted bilayer graphene are so interesting is because there's some magic angle where there is physics of the many body physics and correlated material takes place. There are many, many papers out there. These are just some vignette, but the idea is that those structures are very important. And what I'm going to show to you today is that the relaxations, the atomic relaxations is very important to do this. So our goals in this work is to calculate the Phonon on twisted bilayer graphene, and we want to look at very large structures, and we want to look many different angles. In fact, we look at 692 structures, up to 20,000 atoms per structure. So we want to do something that can be reliable, fast, and also accurate. And I was convinced initially with this project that we would be able to make a one-to-one correspondence between the twist angle and the shear and breeding mode, and we will see that that might not be exactly correct. So first of all, we have to be able to build superstructures, supercells, and we are interested in periodic system because we don't want to have to bother with edge effect and finite size effect, so we want to have commensurate structures. Not all structures are commensurate, of course. Only some angles are commensurate, a very large number. And in fact, the twist angle that lead to a commensurate structures are given by this formula, where U and V are coprimes. So we can apply this formula for very simple cases of U equal 1 and V equal 0, and we get the AB stacking, and we can have U equal V equal 1 for the AA stacking, and so on and so forth. So we can build that. And then we stop when the structure has more than 20,000 atoms. And this is the structure that we get 692. We get 692 structures that way. So here I'm not going to show you the 692 structures. I'm sure that you are probably thankful about that. But here are just another 12 structures that we obtain. And again, the solution of this coprime idea. And each pair of coprimes lead to a commensurate structure. For this work, we use the Ribot potential, which is a force field. So we could not use DFT because we have, as I said, many structures, very large structures. Ribot, so the reactive force field for in this case for carbon, is fairly accurate at finding the phonons and the properties of graphene materials. I should just say that some effect like cone anomaly or even something that happens in some of the bands, the higher bands, is not that great with Ribot. And also the actual absolute value for the G band. So the G band is this particular peak that is actually around 1600 wave numbers experimentally, is much higher, is quite a bit higher in Ribot. But the physics that we want to look at turns out that of the relaxation turns out to be fairly robust. But we have to keep in mind of course the caveats when we do a calculation like this. So one thing that we found also important is to describe the van der Waals interaction very well. It turns out the Lennard-Jones potential does not yield something satisfactory. In fact, we found that when we have even a supercell with AB stacking, this Lennard-Jones potential will create buckling. So we instead, we use the Kolmogorov-Crespi potential, which has been developed especially for carbon material. I believe it was developed for multi-wall carbon nanotubes, and that's what we used. There is quite a bit of technical details related to how we do this, and I invite you to look at the reference in the 2D material paper I mentioned before to see them. The point is that we can do relaxation, and we find that indeed there is quite a bit of relaxation, especially for small angles. So those two plots that I show you here are plots. Each dot is a different structure, so all the structures that we looked at. And we see that at a very small twist angle, we have quite a bit of reconstruction, either lots of displacement of the atom. You see quite 0.2 angstrom, it's quite large, and a change in layer separation as well. And so what happens is that when we look at that, we do realize that, of course, something happens mostly below 5 degrees. This is where lots of things will happen. There is another way to look at this, is to look at a map for a specific twist angle and see where the deformation takes place. And you see that the deformation, you start to have corrugation because the deformation are not uniform. That's the reason why you have these things here in the displacement and the separation that have those values that are changing. You see that what happens is that you have quite a bit of change in interlayer distance. For example, you have here a corrugation of 0.24 in this particular example. So you have quite a bit of buckling happening due to reconstruction and due to the van der Waals interaction. So the conclusion is that you cannot just simply do these calculations without careful relaxation first. And so what happens in this particular system is that what the system tries to do is to maximize the number of stable A, B, and BA stacking while minimizing the number of AA stacking, which are the least stable. Of course, because of the twist angle is imposed, you cannot get away with AA stacking, but the structure is going to try to minimize the constraint, and by doing this will lead to reconstructions, as I mentioned a minute ago, but also to the presence of this network of boundaries between the AA stacking, the AB and BA stacking. And those boundaries is what we call solitons. So those boundaries create, if you will, some sort of potential, a periodic potential that's there to minimize the constraint. I should also add that all the relaxations that we've done were done by relaxing the lattice constant as well, because the constraint is not just within the cell, but can also be pressure from the other cell. So we had to take care of that. And of course, we had a wonderful tool with the phonons because we were able to check if indeed we had a stable situation by monitoring the fact that the dynamical matrix was positive definite. So this is another picture of what I just mentioned to you between those domains between AA, AB, and BA, and those transitions between those different domains are called the soliton network. So this is very good. Now that we have all this we have this very important aspect done, which is the reconstruction. We can calculate phonons. In fact, we calculate phonons at the same time, but now I can show you phonons. This is one example, 14,000 atoms. And if you calculate the phonons of this, as you know, the Brillouin zone is, the size of the Brillouin zone is inversely proportional to the size of the real space cell. So the Brillouin zone is extremely tiny in this case. And if you calculate the mode, you find that in a very small Brillouin zone there, you just have a collection of points. Of course, there are 42,000 of them. You can't learn anything from this. That's the reason why one of the big aspects of this project was to work on unfolding the phonons into the primitive Brillouin zone. Now, unfolding, the method for unfolding, we adopted the one from this paper from Phil Allen that's referenced here. And this idea is to look at the Brillouin zone in red of the supercell and to try to map the state into the Brillouin zone of the primitive cell, of the cell of AB stacking cell, if you will, which is shown in black. And this is done by looking at a number of projectors and translation operators. And you know how the likelihood of one state to be projected in another one. So this is complicated when you have so many bands and so many normal modes, but that's something that was doable and that Michael Lamparski completed. So we want to map this large supercell into a unit cell, and this is what we get. We get from this unreadable structure into something that starts to look like the band structure of graphene. So let's have a look at that. So this is the AB graphene. This is nothing special. I already showed this to you before with Rebo. And this is what we have when we look at the magic angle. So the magic angle is that angle that people doing electronic properties look at, 1.085 degrees. And what we found when we did this is a few things. First of all, yes, there is a little renormalization of the shear and breathing mode, but the main thing is the presence of those splitting that happens at the high symmetry points. Further, if I look at the very same structure, but unrelaxed, but still with the correct potential, we see that all those splittings go away. So it looks like the relaxation of the structure has a very deep consequence on the phonons and what's happening in the high symmetry point. So let's look at this a little bit further. So these are the results I already showed you before. If I look at a slightly smaller angle, like shown here, we do see, again, splitting that's similar, but it's actually slightly different if you look very carefully, and I show you a picture in a second to show that it changes a little bit from angle to angle. But if I look at a very large angle, remember the large angles when there's very little reconstruction, I find that back the structure of the AB graphene. So the reconstruction really have something to do with is really explaining what's happening. So this is the same plot I showed before, but in colors. And now what we can do is to plot the splitting at these points. So at the M point, this is the first panel A, and at the gamma point, this is the panel C, and then the very low frequencies around here, this is the panel B. And then again, because we have so many structures, we can see trends. And what we see is that the splitting and the number of splitting and the evolution of those frequencies depends on the angle, with the main effect below about 3 degrees. So those small angles have a very large effect. These are a very large effect on the phonon band structure for those. And after about 3-5 degrees, what we find is essentially the same as the Bernal graphene. I was mentioning the breathing and shear mode, they would be on panel B. So you see that there are some variations with angle, but they're not as straightforward as one might hope. Okay, it's time now to focus on understanding the splittings. It turns out that now that we have all the ingredients in our hands, we can start to derive a model now that we've done the computational experiment. So remember, we have this. Well, it turns out what happens is that this can be seen as graphene on top of which we have imposed a potential that has the periodicity of the Moire pattern. And this is actually exactly matches what is called the Frankel-Kontarova model, where we have this kind of springs interaction between neighboring atoms, along with this idea of an additional potential that we have there. This is the Frankel-Kontarova model. And when we have this, we realize it can be seen better here, if you will. It's like the periodic, the sinusoidal potential does not have the exact same period as the lattice, the one-dimensional. We can solve this one-dimensional exactly. In fact, we can solve the two-dimensional exactly as well. My former postdoc Benoit Van Troy has done that, and it's being prepared for publication. But the point is that when you do that, you can develop a model that's called a nearly free phonon model, on which you have a free phonon which is perturbed by the presence of this soliton potential. And this soliton potential comes from the existence of those solitons I explained before, which is basically the grain boundaries, the boundaries between the AA and AA stacking. So there is the Frankel-Kontarova model predict two things. Is a shift of this band, which is basically the presence of the breathing and shear mode, and then the splitting at the high symmetry points. So it's interesting to compare this with the near free electron model that we study as undergrad in solid state physics, where there is this Bragg reflection at the zone boundaries. So this is basically something that is a one-to-one correspondence, even though not exactly, because the potential is bound in one case and it's not in the other case. So let's not worry too much about that in this talk. But this explains why, in the case of phonons, we don't have just one splitting, but we have multiple splitting at the Brillouin zone edge. And those splitting can be explained by the soliton network, the soliton potential in the Frankel-Kontorova model, and these are exactly correspond to this splitting that we see here. Now you can wonder, is all that correct? Is all that measurable? Well, the good news is yes. This is a work that we just published. It was a work led by the group of Professor Jorio, in collaboration with Professor Charlier's group as well in Louvain. And so in this work, the experimentalists, what they did, which is a fantastic experiment, they use a tip-enhanced Raman spectroscopy to actually interrogate the local density of vibrational state in twisted bilayer graphene. So the kind of experiment that you can do in that case in the nano-Raman is to get the local density of state for a given branch. And then you see here, you may say that the resolution is pixelated, but the resolution is actually tremendous. It's about, you know the vibration within a 10 nanometer pixel there, the 10 nanometer side pixel. So that's very, very good. And of course the Moire patterns are very large. So it turns out that we can compare that with Michael Lemparski's work directly by comparing, for example, for the G band. And so what we find is that those things can be explained, those properties, those features and symmetry of the local density, the projected density of state of the phonons have a one-to-one match between the experiment that's shown here and the theory that actually can obtain those local density of state using the methods that I describe in this talk. The fact that we know the relaxation of the structures also allows to calculate the electronic properties more accurately, and this is work that was done by Viet Hung and Nguyen in Jean-Christophe Charlier's work, and he has delivered a talk as well in this Graphene Online 2021. I'm not going to talk too much about this, but the fact is that the fact that we measure, that the ADO's experiment measures those phonons is also related to electron-phonon coupling, which can be explained by looking at the electronic properties as well, which I am not doing in this talk because of time. So it's time to get to conclusion. We studied the phonons in layered materials, look at the twisted bilayer graphenes, and we found that there's a lot going on, especially at small angles. We explained pretty much all our computational observation by the formation of solitons, the Frankel-Kontorova model, and provided a nearly free phonon model to explain the appearance of those splitting. There is a good match with experiment as well, which is of course always useful for a theorist to do. One thing I didn't talk about is machine learning. We actually had done a lot of work in machine learning to be able to predict the angle of a twist based off its Raman spectrum, and this is work that was done by Natalia. I didn't get a chance to talk about it. It's a work that she published in the journal Carbon in 2020. This is a very promising approach to being able to basically use machine learning to find important properties of twist bilayer, and using all those properties of splitting and low frequencies as well. So one thing that I like to say before I end this talk is to mention this new journal that we launched about 6 months ago on the science of carbon. This is kind of a journal that we come from the journal Carbon that you probably know better. So I'm the editor-in-chief of that journal, and then we are very happy to publish all the work related to carbon, and theory, experiment, computation. All these are welcome. I'd like to thank you very much for your attention, and if you have any question, you can always send them to me by email, which is provided on the first slide of this talk. Thank you.